So for number 2 here, determine if the group is cyclic. If the group is cyclic, find all its generators. If the group is not cyclic, list all the subgroups. Okay, so what did we need for it to be cyclic?
Essentially, with the generator, if you multiply the generator by itself enough, it will come back to the energy for itself.
You should have an order. One of these has to have an order of 4, doesn't it? Okay, so we're going to start with 2. And if you want to, let's make a Cayley table for this one. 2, 4, 6, 8. Mod 10, so this is going to be 2, whoops. This will be 4, 8, 2, 6. And then this one's going to be 8, 6, 4, 2. And this one's going to be, well, we know this is going to be 2, 6. And this is going to be 4, 6, 8. This will be 2, 8, 4. All right. By the way, what's the identity of this one? Yeah, and the reason it's the identity is because 6 is where the rows are the same or the columns are the same. So the identity equals 6. We need to find that first. So we stop when we get to 6. So 2 to the second is going to be 4. 2 to the third is going to be, what is that, 8. 2 to the fourth is going to be 16. No, 2 to the fourth, yeah, 16. So there you go. How many times did it take to get there? 2, 3, 4. This one's in order 4. And is it cyclic? Is the whole thing cyclic? Yeah. I think we could prove this too, is that, didn't we prove this with closure too? That it was closed on the Cayley table? Thought we had that. Then if we go 4, 4 isn't 6. 4 squared is 6. So this is going to be in order 2. 6 squared is what? 6. So that's an order 2. And then how about 8 squared is 4. 8 cubed, 8 4 will be 2. 8 to the fourth is going to be 6. So this is also an order of 4. So what are the generators of these two? 8 and 2, yeah. So the generators are going to be 8 and 2. And then we found those. And if the group is not cyclic, list all of its subgroups. Okay, well, it is cyclic, so we got that. You try this second one down below here. You try that one. Quick correction here, number 6 here. 6 is, good catch. 6 is the identity. So therefore it's order 1, yep. So there's 2 order 4s, an order of 2, and an order of 1. For the second one, 1 is the identity, right? For multiplication. Is 1 a generator? Yeah, this is not a generator. Because you can't generate the other ones by multiplying by 1. 1 times 1 is 1. 1 times 1 is 1, 1. 1, 1, 1, 1. They'll always be 1. But 3, you should be able to, let's see. 3 squared. 3 squared is 1, so that has an order of 2. 5 squared is 1, so that has an order of 2. And then 7 squared is 1. That's going to have an order of 2. So what can you say about this group? Do you see any order 4s? No. So it's not cyclic. Now it says if it's not cyclic, list all the subgroups. So what would all the subgroups be? Well, it would be 1, 3, 5, 7, 1, 3, 1, 5, 1, 7, 3, 5, 3, 7, 5, 7, and then 1, 3, 5, 1, 3, 7, 1, 4, 1, 5, 7, 3, 5, 7.
If you have like 1, 3, 5, that includes 7 in the data table. I mean, that's not part of the group, so it's not closed. That's like 3 times 5 is 7.
That's true. Well, so probably the only groups that you would have would be this one and this one.
I think it's like which each thing cycles through. And the thing is that you only really have everything cycling to 1. So you have the entire group, and then each individual value is 1.
Right, so like 5, 7.
Okay, so as we're looking at this one, I'll get there. As we're looking at this one, as far as the subgroups are concerned, we have 1, 3 as a subgroup because you have 1, 3, 3, 1. And you would have 1, 5 as a subgroup, 1, 5, 5, 1. You'd have 1, 7 as a subgroup, 1, 7, 7, 1. But you couldn't do 1, 3, 5. That wouldn't work. It wouldn't be closed. And or 3, 5, 7. It would have to be all of them, 1, 3, 5, 7, to be closed again. So these are all the subgroups. Does that make sense? Cayley table, super helpful with this one.